This video pertains to problem 3 and problem 4, t-testing for the true mean. T-testing for the true mean is conducted when sigma is unknown. So they are going to wish for us to work with sample standard deviation or find sample standard deviation. When you turn your attention to t-testing for the true mean, there are a couple of things you need to keep in mind. First of all, in terms of setting up your problems, you still have these three: a two-tailed t-test, a right-tailed t-test, a left-tailed t-test for the true mean. But when it comes to certain things like finding critical values, using alpha to find critical values, and using the test statistic to find the p-value, you cannot use the z-table. You must use the t-table. That means no more invert norm, no more normal CDF. You cannot do that with the t-test or the t-table. You are using the student t distribution with all of its properties. Do not go to invert norm or normal CDF. You will have to use the table. Other than that, the way that you go about setting up a test that's a t-test is pretty much the same. We're going to read the problem and we're going to pick out what's given and what they ask us to find. And we're going to analyze the first sentence and the last sentence. A researcher estimates that the average height of buildings of 30 or more stories in a large city is at least 700 feet, period. Researcher estimates average height at least 700 feet. I wonder if that's what we're going to test, what he's testing or she's testing. Let's see. A random sample of 10 buildings is selected and the heights in feet are shown below. At alpha equals 0.025, is there enough evidence to reject the claim? Now let's read that again. At alpha equals 0.025, is there enough evidence to reject the claim? But it leaves me wondering what claim. So we'll read it again. A researcher estimates that the average height of buildings of 30 or more stories in a large city is at least 700 feet. That's coming from a researcher. A random sample of 10 buildings is selected and the heights in feet are shown. At alpha equals 0.025, is there enough evidence to reject the claim? The only claim that this particular sentence can be referring to is that of the researcher. Nowhere does it say, is there sufficient evidence to support the claim that the average height is less than 700 feet. It just point blank says at alpha equals 0.025, is there enough evidence to reject the claim? What claim? The researcher. So this is that rare example where what your claim is and what you're testing is your first sentence and it's also your last sentence. So the researcher says average is at least 700. If you do not know what at least means, go to your phrases, pick out the symbol or the verb, the verbiage is at least, and the symbol is greater than or equal to. So I'm going to say, okay, the last sentence says that after this researcher estimates this, that it's at least 700, a random sample of 10 buildings is selected and the heights in feet are shown. At alpha equals 0.025, is there enough evidence to reject the claim which is made by the researcher? So mu is greater than or equal to 700 is the claim. That's what we're going to test. First sentence and the question itself agree. Okay, so then we got to set the problem up, and if you look for your claim symbol of at least, it is always the null statement. in this situation. And then that makes the alternative less than, and the hypotheses are opposite each other, as they should be. So I'm going to cut this out and paste it down and not change my symbols or the name. Null versus alternative. The null would have to be this, and the alternative would have to be this. You cannot change anything. The claim this time is the null. Yes, the claim can be the null. It can be the alternative, but not both at the very same time. So let's write down what's given. A random sample of 10 buildings is selected, and the heights and feet are shown. Alpha, I guess set by the researcher, is 0.025. This problem is raw data, and so we have to find X bar and we have to find S. That means it's a t-test and not a z-test. Sigma is unknown. No matter how many times you read this paragraph, they do not say, well, by the way, the population standard deviation is so-and-so. If they do, it would be a z-test. Nowhere do they even mention find the sample mean, find the sample standard deviation, but it's implied because it's raw data, and they never mentioned a standard deviation from another population anywhere, that you better find S and use it instead. So this is a t-test, not a z-test. In particular, it's left-tailed because the alternative less than points to the left. Critical value time. We are going to draw a t-axis, bell-shaped curve. We are going to shade the left tail, and we're looking for a negative t. That is our critical value because it's a left-tailed t-test. Our one and only critical value is going to come from the t-table, and it's going to be negative. And then we're going to use our alpha to help us, but we're also going to do something else. We're going to need something called degrees of freedom. So we are going to isolate row 9. T-table time. Going to the t-table. If you lightly crossed out 1 tail alpha, 2 tail alpha when we were doing confidence intervals, because I said it might be good to do that so that you don't see all those numbers and you just see your degree of confidence for confidence intervals. If you crossed them out, now you want to cross out degree of confidence and look at 1 tail alpha versus 2 tail alpha. If you are conducting a left-tailed or right-tailed t-test, you'll know it, and you'll look up your alpha here. If you are conducting a 2-tailed t-test, and you'll know it from your setup, you'll look up your alpha here. We are conducting a left-tailed t-test for the true mean. So we're going to look up our alpha here, and it falls at 0.025. And then we go to row 9, and we have 2.262. If you notice, all the values in the t-table are positive, but there are plus and minus t values. We just make this negative, a negative 2.262 as our critical value. So row 9, degrees of freedom, not row 10, and this column 0.025 in the 1 tail alpha row because it's a left tail t-test. Look up your alpha here, and that was our given alpha, row 9. And we have to know more than the table that this is a left-tailed t-test, so we're going to have to make that a negative. So this particular critical value is a negative 2.262. Negative 2.262. And if you look over to the side at the table, you can see plus and minus t, a left-tailed test, a right-tailed test, and a 2-tailed test. But the way I find the critical value is different in the t-table compared to the z-table. I always go to my degrees of freedom, and I look up my alpha. I don't divide alpha by 2 if it's 2-tailed. I just go to the 2-tailed row if it's a 2-tailed t-test and find the alpha they give me. If it's a left-tailed or right-tailed t-test, I just look up the alpha they give me. And then when your two fingers meet, that's going to be your critical value. So since it's hard to see, I'm going to write this off to the side. Your CV is a negative 2.262 for this problem, and it better be negative based on where it's located, and it's a left-tailed t-test. Test statistic. T is equal to x bar minus mu s over the square root of n. Well, guess what? We haven't calculated our raw data. So I'm going to take the time to put our raw data in the calculator. I am going to clear out column L1 and just start putting the numbers in the calculator. 485, 520, 511, 535, 841, 635, 725, 616, 615, and 582. 485, 520, 511, 535, 841, 635, 725, 616, 615, and 582. Looks good. Then go to Stat, arrow over to Calculate, one variable statistics, and I need to change that to the L1 column, and then Calculate. So my mean is 606.5. Our raw data values were whole numbers, so if we did round, we'd round to the nearest tenth, but we don't have to because it's exactly 606.5. The S is going to be 109.1, rounded to the nearest tenth. So I'm going to write that information down, and I'm going to go back up here, 606.5, and approximately 109.1. And then we can plug in here 606.5 minus 700, all divided by 109.1 divided by the square root of 10. And it's going to be a negative test statistic. Divided by, parentheses, 109.1 divided by the square root of 10. Negative 2.710. And you'll round to three places because it's coming from the t table. Negative 2.710. Favorite part is putting it in the picture, negative 2.710, and our test statistic was a negative 2.262. So we have to think about, is it going to fall in that left tail? Is it going to fall in that rejection region or not? So think about, is it smaller than the negative 2.262 or is it larger? So negative 2.710 would have to be in the tail, because it is smaller than negative 2.262. So there's where it falls. Because I don't have room to write it on the axis, and it is on the axis, I'll write it here. Therefore, with this problem, we are going to reject the null statement. Because of where the test statistic falls. Again, reject the null, and the null says that the average is at least 700 feet. And yes, that's our claim, but I'm going to go to my diagram to figure out what my summary statement will be. Reject the null is our decision. This time our claim was the null, that it's at least 700, and we decided to reject the null. My claim is the null, and we rejected the null, so what does that mean? Claim is null, reject the null. There is enough evidence to reject the researcher's claim that the average height is at least 700 feet, sadly. So I'm going to write that down. There is enough evidence to reject the researcher's claim that the average is at least 700 feet. I didn't write all of that out, but there is enough evidence to reject the claim that the average is at least 700 feet. And that's all you can say. Since we rejected the null, the type of mistake or error made would have been an alpha or a type 2, rejecting the null when it could have been true. So that's a possibility of a mistake. Now, p-value method. We have the same setup, at least 700, which is the claim. It's the null statement, versus less than. Still a left-tailed t-test for the true mean. The test statistic is a t equals negative 2.71. Let me write that again. Negative 2.710. Okay. When it is a t-test for the true mean and you're using the test statistic to find the p-value by hand using the t-table, you cannot find a specific p-value like we did before when it was a z-test. We have to find something called a p-value interval when it's a t-test. We still use our test statistic to find the interval from the t-table, but we cannot find a specific p-value. So what we're going to end up with is having a p-value in the middle, less than, and we're going to have it between two numbers. What can it be, possibly? But we cannot give the specific p-value, even though computers and calculators can, which I'll show you, give a specific p-value by hand and table. Before they use calculators and computers a long time ago, they could only use the table. So this is the deal. You go to the t-table and you are going to wish to block off row degrees of freedom, which in this case, again, we want to block off row 9. So the test statistic and block off row 9. You first begin by blocking off row 9. And make sure you're in the t-table. What you're going to do is you're going to think about the fact that your test statistic was a negative 2.710, and all of these numbers across this row are positive. All the numbers in the t-table are positive. And this was our test statistic. By the way, sometimes I say T period, S period for test statistic. We want to take its absolute value, think about it, which is a positive 2.710. And we want to look across the row and find the two values, if any, that bound the absolute value of my test statistic. The only time you're going to have to worry about taking the absolute value of the test statistic is when it's a left-tailed t-test. When it's a right-tailed, then you're good. You don't have to worry about absolute value. It's already going to be positive. Now, going across, you will see 2.710 is going to fall between this value and this value, a 2.262 and a 2.821. And that's that positive 2.710. Positive test statistic falls between them. This is what you do to get your p-value interval. You race to the top, because this is not your p-value interval, these two numbers. You race to the top and you stop where you identify your test. If you identified your test as a two-tailed t-test, you would stop here. If you identify your test as a left-tailed t-test or a right-tailed t-test, you would stop here. We had a left-tailed, so we stop here. 0.025 is larger than 0.01. So I tell students, as a mnemonic device, cross fingers, so that you will remember when you write your p-value interval, 0.01 comes first as the lower, and 0.025 comes last as the upper. So, find the two values that bound the absolute value of your test statistic in the appropriate row, degrees of freedom. If you find them when you find them, you race to the top. If it's a left-tailed t-test, go here, cross fingers. So the possibilities of our p-value are as follows. when we crossed our fingers. So whatever our p-value is, our p-value is going to be between 0.01 and 0.025, whatever it may be. Now, if you're thinking you need a specific p-value to make your decision, you don't. I can take any possible p-value in between these numbers, not including these numbers, and use it to compare with the alpha that I'm given. So you could select, for example, I know that the number, one number that is between them would be 0.0135 because it's greater than 0.01. It's less than 0.025. So that's one example, and it only takes one possibility to list here to compare. Again, if alpha is larger, reject the null. If alpha is smaller, do not reject the null. When you go to your page, you either put in greater than or equal to or less than. 0.025 is larger than any possible p-value between these two numbers. So alpha is greater than or equal to, because I'm following what my sheet says, even though it's strictly greater than. Students want to just put greater than, and I guess you can, but I go by my sheet and put greater than or equal to. And then that says to reject the null statement. So I'm going to arrow back here. Reject the null that says at least 700 feet. There is enough evidence to reject the claim that the average is at least 700 feet, is the summary statement. So the same summary statement. Now your calculator will give you an exact p-value if you calculate a t-test. So you will go to stat and arrow over to test, and you will go down to number 2. This was a raw data problem, but I don't do that. If you wanted to, you would click on raw data and tell the calculator where you put your data. I never do that. I am going to want it to match up closely with what I got by hand, so I'm going to treat it as a statistical problem. The claim number in my setup is 700 feet. The average was 606.5, and I don't want to use the exact standard deviation. It's not going to match up with what I did by hand, so I have to round to the nearest tenth, and that's 109.1. Sample size was 10. And what was our alternative hypothesis? Was it not equal to? Was it less than? Oh, here it is. Less than, which indicates a left-tailed t-test. Enter in on that once you hover over it, enter, to lock it in as a left-tailed. The test statistic t is negative 2.710. The p-value is 0.011996591. When you round that to 4 places, though, because the 5th decimal spot is a 9, it's going to give you a neat response. Now I'm going to write this down on paper. So there's your p-value. 0.011996591. And if you round that to 4 decimal places accurately, your p-value by calculator is 0.0120. Calc. And you could use that here also. You don't have to just decide, choose one in between, and it could be any random number in between to make the comparison. We just chose 0.0135, and obviously that is not the p-value, the one that we selected in between. Everything in between is just a possibility, but the calculator computer gave us an exact p-value, which we rounded to 4 places. So alpha still larger, reject the null hypothesis, and that's a left-tailed t-test. Next test. Last t-test problem for this video. A U.S. web usage snapshot indicated a monthly average of 36 internet visits per user from home, period. Okay, that's my first sentence. And when I go over this problem, please know that I do not understand what the US Web Usage Snapshot actually is. But whatever it is, it indicated a monthly average of 36 internet visits per user from home, period. A random sample of 24 internet users yielded a sample mean of 42.1 visits with a standard deviation of 5.3, period. At alpha equals 1% level of significance, can it be concluded that this differs from the national average? And you see I put a 36 here because I feel like the problem where I found this problem from the textbook, they should have written from the national average of 36, because up here when they stated a US Web Usage Snapshot indicated a monthly average of 36 internet visits per user from home, they should have indicated that was a national average. They didn't indicate that this was a national average. So down here, when they said, can it be concluded that this differs from the national average of 36, they should have said of 36, so we could see the connection. Now, first sentence says the average is 36, obviously. Didn't say less than, greater than, at least, at most. It's point blank. Monthly average of 36 internet visits per user from home. Last sentence. At alpha equals 0.01 level of significance, can it be concluded that this differs from the national average of 36? Okay? If you don't know what differs means, look it up. Differ means no longer equal to. So we have the first statement completely different from the last statement, which our last statement is a question. So that indicates that that's what we're testing if we're trying to answer that question. So this is your claim. Differs from 36. So I'll put that here. Okay. When you go to your packet, once again, to identify your claim symbol, it's the alternative and the null is equal to. So you have no choice but to say equal to 36 versus not equal to 36 or differs. So the claim again is the alternative here, not the null. This was coming from some US Web Usage Snapshot saying that the national average was 36. Somebody must be claiming that they beg to differ and they feel like it differs from 36. Because the question is, can it be concluded that it differs from 36? It didn't mention who was doing this, a researcher or a student, but the question said, can it be concluded that it differs? If the question said, can it be concluded that it is still 36, the same as what the US Web Usage Snapshot says, can it be concluded that it still equals 36? Then we would be testing this null statement. But it doesn't say that. It says differs. Okay, so they take a sample of 24 internet users with a standard deviation, and that's S. Because in the sentence, a random sample of 24 internet users, they yielded a sample mean of 42.1 visits with a standard deviation of 5.3. That standard deviation in that sentence, referring to the sample mean of 24, is a sample standard deviation, which modifies the sample of 24 internet users. So that is sample standard deviation and sample mean. So this is a two-tailed t-test for the true mean. Two-tailed t-test for the true mean. Sigma is unknown. We're using S. Before we did a left-tailed, now we're doing a two-tailed. So out of the three, I am not representing a right-tailed t-test in the packet. So make a mental note that you need to see and work a right-tailed t-test problem for the true mean. because it's not in the packet. We did a left tail, now a two-tailed. Critical value time. You are going to draw your t-axis, bell-shaped curve. You shade both tails. You're looking for a positive t and a negative t to mark your critical values. Degrees of freedom will be row 23, not 24, but 23. You go to the t-table and you isolate row 23. You look at the very top and you have to decide, was this a two-tailed t-test or a left-tailed or right-tailed? Well, it was a two-tailed. So when you go to look up the alpha that they give you, and I have to remind myself, alpha was 1%. Look up the 1% in the two-tail alpha row, which is here, because it was a two-tailed t-test. And row 23, not 24. Where your two fingers meet, you get plus and minus 2.807 for your two critical values. Plus and minus. So this was a two-tailed t-test. Look up the given alpha here of 1%. They gave it in the word problem. Level of significance. Degrees of freedom, 2.807. So I'm going to write that down in the picture. This will be a negative 2.807 and a positive 2.807 as my two critical values. Test statistic. This is going to be, what was the sample mean? I forgot to write it up here above. It was 42.1 from the paragraph. Sample mean of 42.1 with a sample standard deviation of 5.3, talking about that sample of 24 internet users. So we have 42.1 minus my 36 divided by 5.3 divided by the square root of 24. And that's going to be a positive test statistic. (42.1) minus 36 divided by parentheses 5.3 divided by the square root of 24. Arrow over. 5.638 is your test statistic. 5.638. And that is here also. We're going to need that in a moment. Now you put your test statistic on the axis where it falls, and obviously it has no choice but to fall in the right tail on the axis because it's larger than that positive 2.807 critical value. Reject the null. What do you know? And the null said, just so I can remember what I'm rejecting, it said it was 36. It was equal to. So we were rejecting that null statement. Now summary time. Our claim is the alternative, that it differs from 36. Our claim is that it equals 36. And so if you have to still go to the diagram, go to the diagram. You may not have to after a while. Maybe you'll know this by heart. There is enough evidence to support the claim that the national average differs from 36. The claim was the alternative, differs from 36. We rejected the null that said no, that said equal. We rejected the statement that said equal to 36. There is enough evidence to support the claim. So that's pretty good. There is enough evidence to support claim that the average differs from 36. Voila. Yay! There is enough evidence to support the claim. Now, p-value interval time. We are going to have to go to row 23 again. Block it off. This time is when you look across the row and try to find the two values that bound your test statistic. So, row 23, and if you look across row 23, our test statistic was a 5.638. Well, these numbers are growing larger as you read across. The largest number is 2.807. This is what we're going to do. 2.807. Test statistic. 5.638. Question mark. Whatever that number is here, what we're going to do is we're going to say that there is some number that falls off the table that is larger than the 5.638. Hence, technically, we now have this number and this number, which is larger, that bound the test statistic, which is positive, by the way, so we didn't have to worry about its absolute value. This same little trick can apply when you go to your top. Remember, when you go and race to the top, it depends on if it's a two-tailed t-test or a right-tailed or left-tailed. This was a two-tailed, so we race to the top and we stop here for two-tailed. We are going to put another question mark here, and if you notice, 0.2, 0.1, 0.05, 0.02, 0.01, the numbers here are decreasing. The numbers here were increasing from left to right. This row's decreasing from left to right. So whatever this number is here has to be smaller than the 0.01. So I would still tell students to cross fingers to let the student know that the question mark, which is smaller and unknown, is still first in the p-value interval when you list it. So it's the lower limit and 0.01 is the upper limit. And this is how you would state your p-value interval. Question mark less than p-value less than 0.01. This is when the test statistic falls off your t-table to the right. So, there is a possibility that you can be looking across a row to find a test statistic and it actually falls off the table to the left. If that situation occurs, I will not ask you the p-value method for that t-test. It can happen. We can figure it out, work it the same way we did when it fell off the right side. But it's a little bit different because if it falls off the table this way, you'd have to have another situation to deal with. So the type of p-method t-test that I will give you on tests and quizzes will only be when you can find the test statistic in the row, find that it falls between two distinct numbers, or if the test statistic falls off the table. I can do that if it falls off the table. Then you imagine there's a number larger that also falls off the table, and your test statistic is between them. So then when you go to the top, these numbers are decreasing. So you imagine there's a number here that's smaller than 0.01. So your p-values are between this smaller number, which we don't know, and this larger number of 0.01 for the two-tailed t-test. So on a test, I will say p-value method for t-test only when you can find your test statistic somewhere in the row, or if it falls off the table this way. I'm going to know if it falls off the table this way, so I would not ask you the p-value method, and I would stress to you on the test or quiz traditional method all the way. And I would be asking for like critical values and not p-values or p-value intervals. So I make that promise. Now, technically, if you give me the p-value interval as a final answer, you will only give this part of it. But I still tell you to do the question mark because that is the way we find p-value intervals. Crossing the fingers is like a mnemonic device. But once you realize that it falls off the table and everything, still state it like this with question mark. But the only thing you know is that your p-value is smaller than 1%, basically. So you will technically, in the end, scratch that out. Now, decision. Alpha is given to be 1%, and the p-value is something less than 1%. It is not equal to. So I am going to select any p-value I wish, possibility. I'll use 0.005. I can use 0.003, 0.004, anything that is in this interval. And that certainly is. And then you see that alpha is larger, greater than or equal to. Therefore, reject the null. Therefore, there is enough evidence to support the claim that it differs from 36. Now, the calculator will give you a specific p-value for this same problem, and then we will be done with this particular video on t-testing. Go to Stat and Test and t-test, and you will go to your claim number of 36. So that's your setup, equal to 36, no longer equals 36, step 1. X bar, sample mean was 42.1. Standard deviation was 5.3 for the sample. Sample size was 24. And this was a two-tailed t-test, or the alternative was not equal to, which indicates a two-tailed t-test. And then calculate. So you have your test statistic t of 5.638, and they give a p-value of 9.7128067 times 10 to the negative 6 power. So I'm going to write that down. So you're moving that decimal to the left 6 places. So your p-value by calculator 1, 2, 3, 4, 5, 9, 7, 1, 2, 8, 0, 67 is the calculated p-value. You can certainly use the calculated p-value to compare alpha here with the p-value. Alpha is way larger than the calculator p-value, so reject the null. When it comes test time, though, and it's a two-tailed t-test like this, I'm not asking for the calculator p-value. I'm asking for the p-value interval. So everybody for a t-test needs to know how to give me a p-value interval from the t-table. Everybody's responsible. Even if you plan to use the calculator, everybody has to find the p-value interval when it's a t-test. I will not be asking for this number at all. This is useful, however, if you want to make a quick comparison of alpha and the p-value you know by calculator to make your decision. Also, one other thing is, and I forgot to mention it with the problem before this one, the calculator p-value will always be in your p-value interval. This number is in this interval. With the last problem, I don't have the numbers. Let me see if I can find that. I can. Here's the last problem we did, the left-tailed t-test. We got a p-value interval of 0.01 to 0.025, and the calculator gave us a 0.0120. Well, 0.0120 is in the p-value interval that we found by table. That must always happen. Your TI-83, TI-84 calculator p-value for a t-test must fall in the p-value interval that you find by hand using the t-table. So it does in this previous problem, and now once again this last problem, it falls there. And that will conclude t-testing. Again, I did a left-tailed and a two-tailed, so you need to see an example of a right-tailed t-test. Thank you very much for listening, and I look forward to the